Hi, welcome to my video. I'm trying to help you out with Unit 3, Worksheet 2. Or if you look on the sheet here, it says Worksheet 2A. Whatever. Okay, what we have here is, in Worksheet 1, we were talking about a qualitative motion map and a qualitative graph. Now we want quantitative. We've got the N in there, we've got numbers. And for some reason, there we go. So, here's how this is going to work. We're going to take a look at this. I'm going to take a look at problem 1. I'm not going to give you the exact numbers for problem number 1, but I'm going to try and give you some help so you can figure this out, because Worksheet 2 really is a set of problems, but it's all based on this same initial graph. So let me just show you how to start this one off, and then when we're done with this, when we're done with this video, you should be able to do the rest of this in fairly straightforward fashion. It says construct a motion map. Now the thing to remember here, this is going to be the thing with the dots and the arrows. So we're going to need to read this particular problem. We're going to get into reading word problems later. It says, this time, while cruising along a dark stretch of highway at 30 meters per second, you see, at the fringes of your headlights, some roadkill on the highway. It takes you half a second to react, then you apply the brakes and come to a stop 3.5 seconds later. Assume the clock starts the instant you see the hazard. So, if we take a look at this, it's pretty straightforward. There's a bunch of words in here that are trying to set the scene. Dark highway, fringes of your headlights, roadkill, whatever. Our first clue, we're starting at 30 meters per second. Then it says it takes us 0.5 seconds to react. Then we apply the brakes and come to a stop. So, half a second to react, apply the brakes and come to a stop. So what we want to do is we want to go through this and answer the questions based on somebody going at 30 meters per second. Half a second after they see something, they step on the brakes. Construct a motion map that represents the motions described above, including position, velocity, and acceleration. Hint: make the dots at 0.5 seconds intervals. Right now, let's never mind acceleration. Let's just worry about position and velocity. Well, a motion map is going to be your dots. So this is where you start the dots. Now, I'm not going to do all the dots for you, but our first dot is at 0 time. Our second dot, first dot, 0 time. Second dot is 0.5 seconds later. That's our hint. And then what happens? Well, we're putting on the brakes and coming to a stop. So as these 0.5 second time intervals go, the distance between these dots will be getting smaller. Now, this isn't exactly right, but this is the kind of motion map you're going to get. But remember, we want them at 0.5 second intervals, and we start off at 30 meters per second, or actually, I'm sorry, this is what we want. We're stopping 3.5 seconds later. So I'm going to need 7 dots here. So 7 dots, and the distances between them are going to get smaller. Then we need to understand which direction we're going, and you should be able to get the arrows on those. Then a quantitatively accurate velocity versus time. Now here's velocity. Here's time. You know we start off at 30 meters a second, so let's get our graph set up. 5, 10, 15, 20, 25, 30. So we can start here at 30 meters per second. As far as these intervals, half a second, 1 second, 1.5, 2, 2.5, 3, 3.5, 4. So it looks like we're going to use all of this graph. So we're going to go constant velocity for half a second. Then what happens from here to there? What happens there? You need to graph that. Go back and look at the problem to figure that out. They give you all the numbers that you need. Graphically represent the car's displacement during this incident. Remember, what is it? What is it about velocity versus time that gives you displacement or distance? And I have talked about this several times. It says utilizing the graphical representation, determine how far the car traveled. Oh, so if we understand what about this graph gives us velocity versus time, we should be able to figure that out. In order to draw an accurate acceleration versus time graph, you need to determine the car's acceleration once the brakes were applied. So you need to go back and remember, what is it about a velocity versus time graph that gives us acceleration? Two kinds of motion occur in this case. For the first half a second, it's constant velocity. For the remainder of the time, the car has an initial velocity and a uniform acceleration. Use appropriate mathematical expression for each phase of the motion. And then compare your answers to 4 and 6. So take a look at what you did for 4. Compare that with what you did for 6 and see if you see anything that's either the same or different. So worksheet 2 is really not too bad. It's the same kind of thing that we were doing in worksheet 1, only we're adding some numbers. If you get these things done tonight and you can show me tomorrow, then I will give some extra credit. Tomorrow, by the way, is actually let me call this Thursday. Right now it's Tuesday that I'm recording this. Let's call this Thursday, the 10th of October. I will give extra credit for showing me that you did this. And we'll be checking out our binders on Friday. Okay, thank you for watching. And I hope all of your problems have solutions.